y bar or the q, so 2 times by 0.02 times by 0.015 times by 0.015 divided by 2 is equal to 4.5 times 10 to the power minus 6. Let me do it again. 2 times by 0.02 times by 0.015 squared divided by 2. Yep, it's correct. And then minus 2 times by 0.02 divided by 2 is equal to 0.02. Okay, y squared. I'll do it again. 2 times by 0.02 times by 0.5. Yep, 0.0. So this will be equal to 80 power minus 6 plus by 4.5 power minus 6 is equal to 84.5 times 10 to the power minus 6, and then minus by 0.02 y squared. Okay. Yep, 4.5 times 10 to the power minus 6, and then 2 times by 0.02 divided by, yep, it's correct. Okay. So now we are going to substitute everything into the equation. Okay, so the shear stress at y, this will be equal to 90 times 10 to the power 3 multiplied by 84.5 times 10 to the power minus 6 minus by 0.02 y squared. And then the whole thing, we are going to divide by 5.813 times 10 to the power minus 6. Now the thickness is 12. It's 2 because of left and right flange, and multiplied by the thickness of 0.02. Okay, so this will be equal to 90 power 3 times by 84.5 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 32.707 times 10 to the power 6 minus by 80 power 3 times by 0.02 divided by 5.813 power minus 6 divided by 2 divided by 0.02, 7.741 times 10 to the power 9 y squared. Okay, that is the shear stress distribution. So how do we know this is correct? So what we're going to check, if we're going to substitute the shear stress, the y is equal to 0.015. So this will be equal to what? Okay, so 90 times 10 to the power 3, or what am I doing again? So we get, let me see, what do we will look at here. We get 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9 multiplied by y squared is equal to 0.015 squared. Okay, so this will be equal to 32.707 power 6 minus by 7.741 power 9 times by 0.015 squared. We get 30.965 times 10 to the power 6 Pascal. Let me do it again. 7.741 power 9 times by 0.015 squared. 32.707 power 6 minus by this is equal to 30.965. Okay. So is this correct? So if we go back and look at our absolute answer for point A, we also got the same, 30.965. And then when we substitute into this expression over here, we also get 30.965. Okay. So now we know, okay, so what we have learned down here, so now we know that the distribution, okay, over here is the distribution, okay, in the web section. Okay. Now, so far, right, you can see that we are focusing on the top half of the structure. Okay. Now, what if now, okay, we derive the bottom half? Let me elaborate. Okay, let me elaborate. So what if now, right, we derive from the bottom, right? So we know that over here, this distance over here is 35. We know that this distance now is 65. What if now we derive based on the shaded region over here? Okay, so from here to here, this is our y. Okay, and then over here, this is our y bar. Let's see what equation we get. Okay, so now we are going to derive the shear stress distribution by focusing on the bottom of the structure. So this is the top, this is the bottom. So now we flip around. Now y, okay, is in that direction. Okay. So now we know that the thickness is equal to twice 0.02. So this is equal to 0.04 meter. And then we know the limit is 0, y, and is not going to be going more than 0.065 meters. Okay, not more than 0.065. So now we have Q, okay, Z as a function of y. The width is twice multiplied by 0.02. The limit is 0.065 plus by y, or minus by y, sorry. That is the depth. And 0.065 plus by y multiplied by half. So over here, this is our width. Over here, this is our depth. And this section over here, this is our y bar. Okay, so this will be equal to 2 times by 0.02 times by 0.065, 1, 0.065 twice times by 0.5. So this is equal to 84.5 times 10 to the power minus 6 minus 2 times by 0.02 times by 0.5 is equal to 0.02 y squared. Okay. Now, have you seen this before? If you look at this expression over here and this expression over here, they're the same. Right? They are the same. Can you see that? Okay. So when that's the case, we also know that the shear stress as a function of y will be equal to 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9, okay, y squared. Okay, so either you use the top or the bottom if your equation is derived correctly. Okay, the answer is the same. Okay, now remember we have earlier we derived an expression that the shear stress as a function of y is equal to 3 over, is it 3 over 2? I can't remember now. Yeah, 3 over 2. Okay, 3 over 2. Okay, Vy over A bracket 1 minus by y squared over by c squared, right? Let me see, did we derive that? I need to be sure that it's the, yeah, v over a 1 minus. So now we know, right? This equation is at its maximum if this is equal to what? 0. So tau max should be equal to 3 over 2 Vy over A. Okay. So we have 3 over 2. Okay, let me write properly. I don't want to rush. Okay, Vy over A. When I rush, that's where stupid things happen. So this is 3 over 2 times by 90 times 10 to the power 3. Next, we are going to do the cross-sectional area. So the cross-sectional area is 0.16, the width, times by the depth of 0.02, plus by twice, right? Twice of 0.02, multiplied by what? Multiplied by 65. Oh, no, not 65. The whole thing is 100, 0.08. Okay. So this will be equal to 0.16 times by 0.02 plus by 2 times by 0.02 times by 0.08. Okay. So 3 over 2 times by 90 power 3 divide by that value. Okay. Hold on. Wait. Something is not right. 0.16 times by 0.02. Right. Plus by 2 times by 0.02 times by 0.08. Right. So it's 6.4. So this is 6.4 times 10 to the power minus 3, right? This is 90 times 10 to the power 3. So this will be equal to 90 power 3 times by 3 divided by 2 divided by 6.4 power minus 3 is equal to 21.094, okay, times 10 to the power 6 Pascal. Okay. Now, this is using the formula that we have derived, the 3 over 2 Vy over A. Okay. But if we use this expression over here, right? If we use expression over here, where when you substitute the shear stress is equal to 0, this will be equal to what? 32.707 times 10 to the power 6 Pascal. Okay. So my advice to you, okay, in when you have a situation like this formula cannot be applied. Okay, this formula over here, 3 over 2 Vy over A, right? This formula over here, we cannot apply it. We cannot use this formula. Any idea why? Any idea why we cannot use this formula? The answer is because of what? In order to use this formula, the thickness, right, has to be what? Constant. Okay. What we see over here, our thickness, okay, is not constant at all. That's why this over here, okay, what we have over here is underestimated compared to here. Because when we derive 3 over 2 Vy over A, 1 minus y squared over c squared, the thickness is what? Constant. Are we clear? Because I've seen some examples that are used by the book later on that they use this formula and it's wrong. Okay, you cannot just use that formula. In that context, I will stop here and I'll see you guys tomorrow. Okay, thank you for your time. Thank you for your attention. I'll still stay behind if you have any questions. Okay.